All right, it's time to look at trigonometric functions from the other perspective. In section 7.2, we approached it from a right triangle perspective. Now in section 7.3, we're going to approach trigonometric functions from the unit circle perspective. So first of all, unit circle. A unit circle is a circle with radius equal to 1 unit. Okay, the word unit in this case refers to 1 unit, and that's the radius of the circle. So if this is a unit circle, in particular, usually when you say a unit circle, it refers to a circle centered at the origin with radius equal to 1. So here I have my x-axis, my y-axis, and then that means if its radius is 1, then these points that it passes through on the axes are all going to be 1 unit away. So this is going to be like 1, 0, and this will be 0, 1, and then we'll have -1, 0, and 0, -1. So there are the 4 points on the axes that this unit circle is going to pass through. All right, now, if you have an angle, and you can take any angle you want, I am going to draw this picture with an angle between 0 and pi/2. So I'm going to draw it with an angle that's in the first quadrant here, but I just want to make clear that this could be any angle at all. If I draw a line like that, it's going to pass through a point on the unit circle. Specifically, this is a unit circle at the moment. It's going to pass through that point. Let's say the coordinates of that point are xy. Okay? Could be any point on the unit circle for any angle, but let's say those coordinates are called x and y. Could be negative values, could be positive values. In this case, in the first quadrant right here, the lengths of the sides, let's see, the lengths of the sides of this triangle that I can draw. Basically, if I drop a line straight down from that point to meet the x-axis at a right angle, I can form a triangle in here, okay? And the lengths of the legs of this triangle are x and y. Now I know if this angle is somewhere in a different quadrant, like if this angle terminated somewhere over here in like quadrant 2 or 3 or whatever, then these would be negative numbers, and they wouldn't exactly be the lengths of the sides. They would be like negative versions of those lengths. But that's okay. Part of the power of the unit circle approach rather than the right triangle approach is because this approach is going to allow us to define the trig function outputs for any angle, not just angles that can appear in a right triangle, because those angles are only acute angles. This is going to allow us to define trig function outputs for obtuse angles or negative angles or whatever, any angle, large angles over 180 degrees. So we're going to allow those values to be negative potentially. Now the hypotenuse of this triangle is always going to be 1, +1, because that's the radius of the circle. So now let's look in here. This is our angle. Okay, let's call the angle T. Okay. And for this angle, opposite the angle T is the y value. Adjacent to the angle T is the x value, and the hypotenuse is 1. So with that information, I can write down what cosine and sine and tangent are. Cosine of the angle T is going to be the adjacent side x divided by 1, which is just x. And the sine of that angle T is going to be the opposite side over the hypotenuse, which is y. And right there is the key idea with the unit circle. If you have a unit circle, it has to be a unit circle, because in order to get the dividing by 1, all right, in order to get divided by 1 here, it had to be a radius 1 circle. So if you have a unit circle and you put a ray coming out from the unit circle at some angle in standard position, the cosine and sine values of that angle are going to correspond exactly to the x and y coordinates of the point on the unit circle where that ray crosses it. So that is a huge important idea. Now, if I do this with tangent of t, I'm going to get opposite divided by adjacent. So that's going to be y over x. And that, y over x, for this ray that's coming out here, it goes up by y for every x it goes over. It's a straight line, right? So y is like rise and x is like run. This is rise over run, which can be interpreted then as the slope of the ray. I think ray, this particular version of ray, I think is with an A. Maybe it's with an E. I don't really know. You know what I mean. It's the ray. Slop. Gosh. Slope. There we go. It's the slope of the ray. So that idea, tangent value, the tangent of the angle, giving you the slope of the ray coming out from the center, from the origin, that is a super useful idea, because then it gives us things like, well, if the slope is 0, the tangent value is 0, right? If you get a vertical ray, that's an undefined slope, so tangent function is undefined. If you put the slope at 1, like a slope of 1, the tangent value would be equal to 1, right? So that correlation there is also really useful. Another thing you can get out of this right here, based on, tangent of, actually just this part here, tangent of t is y over x, you can get tangent of t equals y, which we said was sine, divided by x, which we said was cosine. And that right there, that is called a quotient identity. So I mentioned when I introduced the cofunction identity that we were going to be introducing a bunch of different identities, and this is one of them. That tangent is related to sine and cosine in this way. Tangent is sine divided by cosine. So okay, let's take what we've learned here. In particular, we're going to take the idea that xy, for the point on the unit circle where the ray crosses it, that is equal to cosine of t, sine of t, where t is the angle of the ray. So cosine gives us the x coordinate and sine gives us the y coordinate. Key idea right there. Okay, put a star by it. So let's look at some values. Let's look at t equals 0. Let's see, I'm going to divide this into segments here. When we look at t equals 0, we're going to look at t equals pi over 2, t equals pi, and t equals 3 pi over 2. Let's identify where those are. T equals 0 would be right here, at this point right here. T equals pi over 2 is right up here at the top, okay? T equals pi would be over here, 180 degrees is over there, and then t equals 3 pi over 2 would bring us right down here. So those points where the unit circle intersects the x and y axes, those are the points that are going to tell us the sine and cosine values of these angles. So we can say, knowing that t equals 0 is this point right here, we can say cosine of 0 must be the x coordinate of that point, which is 1. So remembering this information, the x and y correlation for cosine and sine, as long as you know the point on the unit circle that the angle would correspond to, like this is called a terminal point. I guess I could label that. This idea here is terminal point for the angle. If t equals 0, the terminal point is here, and the x coordinate is 1. The y coordinate is 0, so sine of 0 equals 0. And then remember the tangent output is the slope of the ray. So the ray coming out right here, put it in red. This ray here, slope 0. So that tangent of 0 equals 0. Let's do pi over 2. For pi over 2, cosine of pi over 2 is the x coordinate of this point, which is 0. Sine of pi over 2 is going to be the y coordinate of this point, which is 1. And tangent of pi over 2 is the slope. It's the slope of that ray, and up here, the ray coming out, passing through that point, is a vertical line. That's undefined slope. And indeed, tangent of pi over 2 is undefined. Okay. So this is the first instance we've had of a trigonometric function where for a certain input angle, the function is undefined. Not that different from how, like in a rational function like 1 over x, it's undefined at 0 because you would be dividing by 0. And if you look at this quotient identity, sine of t divided by cosine of t, for tangent of pi over 2, it's going to be sine over cosine, which is 1 over 0, right? So the quotient identity would give us 1 over 0. Division by 0 is undefined. That's the whole idea, right? So it all connects together, okay? Tangent of pi, let's go through these. At this point here for pi, the x-coordinate's -1, so the cosine of pi is -1, and the sine of pi is 0. Tangent of pi, since that slope is going to be, that ray is slope 0 again, is again 0. Again, sine over cosine would be 0 divided by -1, right? Which is equal to 0. So bring the quotient identity into the idea, and that works. You know, you can use that as well to justify the same answer. And finally, for 3 pi over 2, you can do cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1, because we're looking at this point. And the tangent of 3 pi over 2 is, again, undefined. So I focused on those 4 points, but we're going to do this same idea with x and y coordinates for any angle. And in particular, we're going to be looking at the special angles, pi over 6, pi over 3, pi over 4, and then a bunch of other angles that are going to refer back to those ones.